Hello and welcome back. Today, I am very pleased to bring you my AI planner that I've been working on for the last year or so called Hivemind. There's quite a lot to talk about, so I'll just jump right in. The ultimate goal of the Hivemind planner is to provide the game environment a way to dynamically respond to player input and world events in a way that is both meaningful and intelligent. In order to achieve this, the planner focuses on solving the following problems: creating a formal representation of thought and decision making. The planner system itself uses an inversion of control scheme where specific drone systems, a technology that will be discussed later, implement a specific paradigm to represent the desired/permissible states the drone belonging to the system can achieve. We want to represent a dynamic world state. Because the planner runs in its own thread separate from the simulation, the representation of the world must both be dynamic and generic. In order to do this, a concept of world state is introduced to give the planner thread the ability to quickly grab drone or object information without regard to type. And finally, decouple action execution from planning. Just like with world state, we're dealing with two separate threads that are attempting to solve one task concurrently. Because of this, the actual code which is executed on the simulation thread is designed to alter and manipulate the simulation state data to bring the planner representation to its desired state. Another technology that will be introduced later is the action generator. These exist inside of drone systems and are created during the planning process. These are passed then to the simulation thread via a runtime database. And runtime databases are outside the scope of this video. However, I will leave a link below where I go over their implementation. The primary inspiration for this project should unsurprisingly come from goal-oriented action planning. While the system is a departure, it can be thought of as a spiritual successor. However, for more information on GOAP, please see the video link below from AI for Games. He gives much more justice to this topic than I ever could. And now we're going to discuss a pretty general overview of some of the more core components to this system. First up is going to be desires. Desires in this system take a more active form than in the traditional GOAP system. A desire represents a state value that wants to be seen in relation to some AI object or drone. And in order to manage desires, they have been modeled as constraints, similar to what you may see inside of a physics engine. Each time an object updates, any constraints it may belong to are evaluated, and should a violation be detected, a desire is generated to alter the specific state back to what we want it to be. Now, at some point, the planner will have to evaluate the state of the objects and drones it's planning for. To achieve this and provide a generic type that any drone system may interact with, the primitive type world state is introduced. World state is a generic data buffer capable of storing up to a quaternion's worth of data. And then finally, in order to keep the drone system paradigm cohesive and decoupled from the external game systems that they will interact with, a drone system only chooses an action in concept. For example, in the combat system, when a plan is created to attack an object, the combat system action simply stores the attacker and target IDs in the combat data system. The final decision about what attacks can or should be performed is handled by the combat module implemented by the game. So now let's move on to talking about some of the supporting technology, beginning with world states, blackboards, and updaters. As mentioned before, world state acts as the generic primitive used to represent some nondescript data about an object. Since nondescript data is pretty useless, a blackboard is implemented to house the state of all AI object representations. When an object has data supplied into the blackboard, a symbol is given with it and hashed to represent this data. All data of a specific representation for AI objects are stored in a sparse map inside the blackboard. This allows systems to be built without needing express knowledge of the data in the blackboard, but rather making an assumption if the object engages the system, its data representation exists. In order to achieve this abstract representation, Upon initialization, a series of tables and updaters are mapped together to tell the Blackboard how to read and write state data. Moving on to desires, aside from the expected routing information, the core of a desire is its comparative value and satisfier/terminator. The comparative value comes as a need to solve an issue that arises when you carry a static desire over many frames. Take, for example, a desire to move the object to the location of the player. If the desire was to cache a static snapshot of the player position, this value would quickly become invalid without some sort of mechanism to update the desired state externally. This problem can be solved from case to case by predefining a desired state update function and calling these functions to update the desired state value. However, because we have already predefined these updaters, we can generalize them into a common interface and store it directly inside of the desire. The satisfier functions very similarly and is derived from the same spirit. Given our example from before, the satisfier may be used to determine if the current position of the object is within some range to the target. The reason for this is twofold. The first being the dynamic update problem, and the second comes from the need to deal with finite precision and tolerances. Whereas the comparative value is used for one-to-one validations, satisfiers determine their validation within a tolerance or range of values. And finally, in order for the planner to be able to know how to solve desires, drone systems provide a series of goals that tell the planner what state representation they operate on, as well as a vector of different details about the actions the system can generate to achieve desired end states on said representation. When a valid action generator is found, it is invoked to create the desired action that will be executed on the simulation thread. Because actions are executed on the simulation thread themselves, directly reading and writing to the simulation or game data systems inside of them creates no race conditions. By separating out action generation from action execution, we can allow the system's responsibilities to remain fairly decoupled. Now, before we can talk about solving desires and executing actions, we need to talk about drones and their systems. The drone system acts as an interface for any system that wants to provide AI functionality to the planner or simulation. The interface itself only imposes that you supply the runtime action details and archetype updaters to a virtual function add runtime. The add runtime function is designed to be called inside the constructor, so registration happens automatically. In addition to this, the interface also provides the ability for a derived system to add the capabilities and attributes that it has. The combination of capabilities and attributes are what determines a drone's permissible actions that can be taken. One note I want to mention about capabilities and attributes is that they are bit-field codes, meaning that they need some level of care when being defined, or else you will attempt to register two capabilities or attributes to the same bit. However, an assertion is done at registration time to stop the program should this be detected. Drones themselves are really no different than any other object inside of the AI world representation. All drones are objects. However, if an object is determined to have capabilities, it is now classified as a drone since the planner conceivably is able to operate the drone to solve any desires matching its capabilities. Constraints, on the other hand, are determined by the object's attributes. The combination of these attributes determine the archetype and is the mechanism used to perform the constraint checks mentioned earlier. The dynamic levers of the planning system are now pulled based on the capabilities and attributes of a drone. Now let's take an example look here at the drone Pathfinder system and see these constraints in action. In order to have gotten to this point, the Hivemind planner would be in the middle of its archetype update loop. The object would have, in this case, the Wanderer attribute assigned to it, and thus the Hivemind invoked the math pathing updater function. As previously stated, we're dealing with Wanderer object, so we call the Wanderer updater. In practice, a random wander point would be computed, but for now, the default player position is used for testing. We'll make sure that the wander constraint is not violated, and if it is, we'll generate a desire that will move the drone to the wander point and be satisfied when it is within some tolerance. We also want the wander to terminate after 2.5 seconds. We make the objective of the desire the object itself. The assigned drone is who will make this desire happen. Obviously, that is the object itself. We're going to make this desire work on the position representation and give it a priority of 0, meaning that if anything else comes up, let's not wander and do that instead. Should the constraint have not been violated, we would simply return the sentinel desire, which is used to signal to the planner to ignore the desire. The actual constraint functions themselves can be anything you need them to be so long as they can be represented in the blackboard. For the wanderer, we just check if the current position and the previous position are not the same. If they are, violation detected. Later on, during desire resolution, the planner will come across these action details and see that the end state of this action returns the comparative value of the desire, which in this case is the target location itself, meaning that this is a valid action generator. The generator will be invoked and called the find mobile route function. From here, the actual pathfinding is performed, the route is generated, and the action to be executed on the simulation thread to make the object move from position is generated and returned. Now, with everything being laid, we can finally move on to the last part of this video, which is desire resolution and action execution. Every loop, after the AI thread processes its messages, a queue is created to store the desire the system currently has. First, each of the current desires the system is already working on are checked for either satisfaction or termination. Should either be true, the desire is removed from the assigned desires list map. If it is not satisfied or terminated, it is added to the desire queue. Once the valid previous desires have been queued, the system then updates each of the archetypes and checks their constraints. Should the constraint return a true desire, as before with the Wanderer example, the system then adds it into the current desire queue. In order to check each of the object attributes, we simply pop off each bit at a time until there are no more bits to check. Finally, once the queue has been created, we attempt to solve a desire per drone that is queued at least one. The queue is sorted by the desire priority, so we'll attempt to solve the most pressing matters first. While we have some desire left to check, we'll make a call to the solve desire function. If the desire is solved, we store the current desire into the assigned desires flat map for long-term storage. If not, we simply move on to the next desire should one exist. Now, in order to solve the desire, we grab each of the actions that the system can potentially perform that operate on the desired state representation. While checking each action, we first make sure that the end state of the action performed matches the desired end state of the drone. If this passes, we next check each of the capabilities that are possible to perform this action. Here, we're only looking for one capability to match, not all of them. Take, for example, a goal where the objective is to bring the target health to 0 or essentially kill the target. The action is simple: attack the target. However, this goal can be performed by a drone that is either melee, ranged, or spell capable. Finally, if the action gives us the correct end state and the drone is capable, we attempt to create the action. Before we can actually create this specific action, we must first assert that all requisite actions leading up to this end state can be performed as well. In our previous example, in order for the drone to be able to attack the target, they must also be able to translate within range of the target. In order to do this, we will loop over each of the requisite states in the action details. Should the state already be satisfied, we move on to the next state. If it's not, we create a new desire using the requisite details and recurse back into solve desire to begin the loop all over. Finally, once the chain of solving desires and creating actions ends, should it be able to find a solution, will contain a sequence of actions that once executed to completion by the drone will have attained its desired state. Should somewhere along the chain the desire be found to not be solvable, the action sequence is rejected and a new solution is attempted. If all possible actions are exhausted, the entire desire is rejected and the system attempts to solve a new desire for the object. After the desire queue has been processed, the action plan will contain the list of all action sequences to be taken by the game objects inside of the simulation. The action plan is pushed into the action plan table, and the planner now sleeps until it's time to reevaluate the world again and generate a new plan. Now that we've exhausted all there is to do on the planning thread, we're going to take a quick look here at the simulation thread and see how these actions are executed. It's actually a very simple function since most of the external code gets called during the forward here. However, we make a very simple loop that we will pull from the action plan table, read each of the actions, and should we be able to perform the next step in the action sequence, go ahead and attempt to invoke the action itself. Now, at the moment, this requisite satisfied field is not used. In the future, more than likely, actions themselves will be changed so that the signature returns a Boolean value to dictate whether or not this step in the action sequence is complete. As it stands, the system is functional as it is. There are some augmentations that can be made in the future to make it better. For example, the cost of performing an action currently is not used. The way I envision it working is the cost performing the action will not be static, but rather dynamic based on the object. After the desire queue has been processed once, while there is still frame budget, more plan options are explored to attempt to find a better solution, not just a valid one. In addition to this, the static cost can also be used as a sorting value for the actions themselves so that they can be placed in the runtime container based on these static values and attempt to find the cheapest options first. Basically, everything surrounding the cost heuristic is to come later on. However, currently, the only other thing that the system really needs is more time to mature. And in order to achieve this, the framework's very first game/engine is being developed. The details of such are outside the scope of this video, but I am pleased to report is going very quickly without much overhead. However, for today, that should just about be everything. The next video to come will either be the maturation of the AI planner, or I will finally force myself to sit down and learn the last few things surrounding the collision resolution process so I can circle back and finish off that series for you all. Nonetheless, thank you for your time, and I will see you in the next one.